All right. Hey there. This is Unit 2, Introducing Q-Learning. This is what they've referenced a lot, and we finally get to learn it. What is Q-Learning? Q-Learning is an off-policy, value-based method that uses a TD approach to train its action-value function. A lot of words there. Off-policy, we'll talk about that at the end of the unit. Value-based method finds the optimal policy indirectly by training a value or action-value function that will tell us the value of each state or each state action pair. Alright, uses a TD approach, updates its action value function at each step instead of at the end of the episode. Perfect, we just learned about this. Q-learning is the algorithm that we use to train our Q function, an action value function that determines the value of being at a particular state and taking a specific action at that state. So in this diagram, they have a Q function. The state and the action pair are going into some Q table, this Q function, that gives us the Q value. Lots of Q's here. To train this Q function, that given a state and that is given a state and action as input, output the value, we use the Q learning algorithm. Okay, so to train the Q function that gives us the Q value, we use the Q learning algorithm. The Q comes from quality, the value of the action at that state. Alright, let's recap the difference between value and reward. The value of a state or state action pair is the expected cumulative reward our agent gets if it starts at this state and then acts according to its policy. The reward is the feedback I get from the environment after performing an action at that state. So the reward is that single feedback, and the value of the state is, the estimated cumulative reward. It's all the rewards with some discount value. Internally, our Q function has a Q table, a table where each cell corresponds to the state action value pair. Think of this Q table as a memory or cheat sheet for our Q function. Alright, lots of Q's here, lots of Q's here. Let's go through an example of a maze. We have a rat, cheese, poison, or cheese. The Q table is initialized. That's why all values are 0. This table contains, for each state, the 4 state action values. So what are the 4 state action values? Okay, so the actions is left, right, up, down. So denoted by this X, left, right, up, down is the 4 values here. And these are all the different states, right? There's 6 states here. So it's 6 times 4. There's 24 values here, and they're all 0 to start. Here we see that the state action value of the initial state and going up is 0. Right? They're all 0, but yes, and going up is 0. Therefore, Q function contains a Q table that has the value of each state action pair. And given a state and action, our Q function will search inside its Q table to output the value. Okay, sounds good still? Yes, the Q function uses this Q table. That's what we just learned. If we recap, Q learning is the RL algorithm that trains a Q function, an action value function, which internally is a Q table that contains all the state action value pairs, or state action pair values. Given a state and action, our Q function will search into its Q table the corresponding value. When the training is done, we have an optimal Q function, which means that we have an optimal Q table. And if we have an optimal Q function, we have an optimal policy, since we know that for each state, what is the best action to take. Alright, the link between value and policy. So this pi star at the state, so this is the policy, is the arg max of this Q star state action pair. So finding an optimal value function leads to having an optimal policy. So we're still value. But in the beginning, our Q table is useless since it gives arbitrary values for each state action pair. Most of the time, we initialize the Q table to 0. As the agent explores the environment and we update the Q table, it gives us better and better approximations to the optimal policy. Right? So first it starts to 0, and then there's some updating process where these are all updated. And you can see that, yeah. You see here that with training, the Q table is better since thanks to it we know the value of each state action pair. Great. Now that we understand what Q-learning, Q-function, and Q-table are, let's dive deeper into the Q-learning algorithm. So what is the actual algorithm that fills in these values? The Q-learning algorithm. This is the Q-learning pseudocode. Let's study each part and see how it works with a simple example before implementing it. Don't be intimidated by it. It's simpler than it looks. We'll go over each step. Okay, so this is algorithm 14, starts and max, Q-learning. The input's policy pi, positive integer num episodes, the smallest positive fraction, alpha, and then GLIE, not sure what that is. And the output is the value function Q, just roughly Q pi if number of episodes is large enough. Okay, so we initialize Q arbitrarily, so this is what we're doing when we initialize everything to 0. So for example, Q of state action equals 0 for all the states and for all the actions. And for Q, I don't know why it says step 1 there. Oh, this is step 1. So step 1 is initialization, right? And then for I, starting at 1 to the number of episodes, so the number of episodes within this function, we are going to do this portion of it internally. So I think epsilon is now I, we observe state, and then t is 0, and we repeat some code, right? This is pseudocode. So choose action A of t using policy derived from Q, for example, epsilon greedy, and we take the action, and then we observe the reward from taking that action, and then the new state, right? So this is the reward, and then the new state. And then we update it, right? So it's Q at that state action pair is now Q at the state action pair plus, the small positive fraction times, this larger term, which is the new reward, plus that gamma term, plus the maximum of, I guess, these two other factors, which is Q of state t plus 1, that action, minus the Q of state at t and that action pair. Okay, and we continue this until the state is terminal, right? So we continue this until it ends. I think in the early example, the mouse either eats the poison or maybe runs out of steps, right? Some terminal state where this game ends. Maybe there's a maximum amount that the mouse can eat. So in step 1, looking at here, initialize Q arbitrarily. So step 1 is this table, right? So we initialize Q arbitrarily. This table is all zeros. So we initialize the Q table. Most of the time we initialize values of 1 or 0. Step 2, we choose an action using the epsilon greedy strategy. So choose an action using policy derived from Q. This is epsilon greedy. So epsilon greedy is, we will probably handpick epsilon, and then in some probability we will do exploitation, and then some other probability we'll do exploration. Right, so here's the epsilon value, and then 1 minus epsilon goes this way, and if you add these two together, then you get 1, right? So this serves as a probability. Epsilon greedy is a policy that handles the exploration and exploitation trade-off. The idea is that we define the initial epsilon, here epsilon equals 1, probability 1 minus epsilon, we do exploration, probability epsilon, we do exploitation. At the beginning of the training, the probability of doing exploration will be huge since epsilon is very high, so most of the time we'll explore. But as the training goes on and consequently our Q table gets better, in its estimations, we progressively reduce the epsilon value since we will need less and less exploration and more exploitation, right? So, how much do you reduce it by? that is going to be a separate issue, but there is this concept that we will reduce exploration, and we'll just continue to reap the rewards of our Q learning table, our Q table. So we perform action A at T, gets reward in the next state, right? So we take this action, we get these, we are going to observe these things coming for us, and then we update it. So remember that in T learning, we update our policy or value function, depending on the RL method we choose, after one step of the interaction. To produce our TD target, we use the immediate reward plus the discounted value of the next state best state action pair. We call that bootstrap, right? So here, the new state is being changed by this former state plus the learning rate, and then this term here, right? This term is the TD term of reward plus discounted value of the next state, right? This is the TD target. Therefore, our Q state action pair update formula looks very similar, right? So Q state action is changed by the former Q state action estimation plus the learning rate times this factor, where this is the TD target. And together, this is the TD error, so this is how much we want to adjust our former Q value estimation by times this learning rate. It means that to update our Q and state action pair, we need state at T, the action at T, the next reward, and the next state. Right? To update our Q value at a given state action pair, we use the TD target. For here, this is the TD target. How do we form the TD target? We obtain the reward by taking the action RT plus 1, and then to get the best state action pair value, we use a greedy policy to select the next best action. Note that this is not an epsilon greedy policy. This will always take the action with the highest state action value. And we're talking about this one, this optimal value. So this is the max of this Q state action pair, right? Because at any state, you can have many available actions to you. Left, right, up, down. But what they're saying is that for the next state, we're only going to take the maximum. Here, these are all zero, so you can't see it, but, for example, we'll never take the poison. Like, that'll never happen unless, the other direction is a worse poison. But we'll never look at the poison because the poison will probably never be the best, right? Unless we're just initializing. But eventually the poison becomes negative, and, great. So then, when the update of the Q value is done, we start in a new state and select our action using the epsilon greedy policy again. This is why we say that Q learning is an off-policy algorithm. Perfect. So what is off-policy versus on-policy? The difference is subtle. Off-policy, using a different policy for acting, which is inference, and updating, which is training. For example, with Q learning, the epsilon greedy policy, the acting policy, is different from the greedy policy that is used to select the best next state action value to update our Q value. So updating the policy. Right, so we choose an action A of T using a policy derived from epsilon greedy, which is different from this update portion, which is here in this formula, where we're just taking the max. Right, this has no relation to epsilon at all. For instance, with SARSA, another value-based algorithm, the epsilon greedy policy selects the next state action pair, not a greedy policy. So here, SARSA and actually here it's called SARSA max, and they're talking about SARSA, I'd assume, not max, regular SARSA. So off policy versus on policy. Off policy, you use a different policy for acting, and for updating. On policy, we use the same. Great. So let's go to the next one, a Q-learning example. To better understand Q-learning, let's take a simple example. So this is still the six little squares. You're a mouse in a tiny maze. You always start at the same starting point. Your goal is to eat a big pile of cheese at the bottom right-hand corner and to avoid the poison. After all, who doesn't like the cheese? The episode ends if we eat the poison, or we eat the big pile of cheese, or if we spent more than 5 steps. The learning rate is 0.1. The gamma is 0.99. Alright, that's a good start. So, yep, that's what we just read. The reward function goes like this. Plus 0 going to the state with no cheese on it, plus 1 going to a state with a small cheese on it, plus 10 going to the state with a big pile of cheese, minus 10 going to the state with the poison, and thus die. Plus 0 if we spend more than 5 steps. If we spend more than 5 steps, plus 0, okay. Should also end. But yeah, that's good. This is that in a better diagram. Okay, so we train our agent to have an optimal policy. So a policy that goes right, down. We will use the Q-learning algorithm. So we initialize this Q table, right? So the Q table is specifically a state action pair related table, right? So on the left side, you see the states, state 1, state 2, state 3, and then on the right side, up top, you see the actions, right? So for now, our Q table is useless. We need to train our Q function using the Q-learning algorithm, right? The Q-learning algorithm is what we saw above, or in the last one. Let's do it for 2 training steps. Okay, so training time step 1. Choose an action using epsilon greedy. Because epsilon is big, 1, I take a random action. In this case, I go right. Okay, perfect. The mouse goes right. Awesome. It doesn't say it here, but this right means I just ate a cheese, right? So right above it, there's a cheese here, and going right means I ate that cheese. Perfect, so this is plus 1. So we perform action t, and we get reward t plus 1, and state t plus 1. So by going right, we got a small cheese, so reward is 1, and you're also in the new state. So you update q at state t and action at t. So now we can update as t using our formula, right? So this is the formula that we had before, and we're going to update it, right? So the updating with the values. So what are the values? So the previous value of this is 0 plus this learning rate 0.1, and the reward, which is 1 because we got that small cheese, plus this discount factor here, it's 0.99, and then the maximum Q value of the next state in A. So what was the next state in A? We know it's 0, but where is it on this map? We know it's 0 because they're all 0, but where is it on this map? So the next state is this cheese state, right? So we know that we went to the cheese state. And what is the best value of this cheese state? Well, they're all 0 right now. Okay, so this is 0, and then we subtract it by 0. All right, training type step 2, this is where it gets interesting. We take a random action again. Since epsilon is big, 0.99, since we decayed a bit because as the training progresses, we want to have less and less exploration. Okay, so I didn't know about the decay, but that's good. There's a decay here. Took the action down. Not a good action because it leads me to poison. Okay, so it shows down randomly, and down is -10, and also the termination of it. So when we perform action AT, it gets reward t plus 1 and state t plus 1, right? And the reward is -1, and I die. So it's -1 plus the whole thing ends. The mouse goes here into the poison, and it's -10. I don't know what the picture of the mouse is. I guess it's gone because of the poison. So step 4 is we update the table again, right? So at this cheese table, what does it mean to go down? Well, to go down, it means the value at this state in the past was 0, and at this cheese state plus this learning rate plus the reward is -10, or multiplied this factor where the reward is -10 plus the discount factor times it was -1. This next state this is -1. It was 0, and the previous state was also 0, right? So when this is multiplied together, -10 times 99 is 99, I guess. Point is 9.9, and then 0.1 times that is 0.99, and then I think this just rounds to 1, right? So we've rounded this to 1. So because we're dead, we start a new episode. But what we see here is that with 2 exploration steps, my agent became smarter. As we continue exploring and exploiting the environment and updating Q values using TD target, Q table will give us better and better approximations, and thus at the end of training we will get an estimate of the optimal Q function. So let's think about why this is smarter. Well, this is smarter because when you're just a mouse starting off, what is a good direction to go towards? Well, everything is 0 because these are unexplored, but going right gives you some estimation that there is a positive reward here, right? So we're at 0.1. Going right may be good. When you're at this cheese, everything starts at 0, and you don't know anything until you went down. And when you went down, you found that actually going down, there's some estimation of it negative, right? So instead of 0, you're at negative. So if you're just given this, right, and you're not even given these 4 pieces of information, you know that this cheese has some danger around it, right? The danger is going down. And the starting point has some positivity around it, and the positivity is going right. So you're getting some directionality of possible benefits, possible dangers, but in this framework, it's positive reward, negative reward, right? They're just these scalar values. Okay, let's do a quick recap. So the Q-learning is an RL algorithm that trains a Q function, an action value function that contains as internal memory a Q table that contains all the state action pair values. Given a state action, our Q function will search into its Q table the corresponding value. When the training is done, we have an optimal Q value, so an optimal Q table. And if we have an optimal Q function, we have an optimal policy, since we know for each state what is the best action to take. So let's think about that, right? So the Q table, let's say we've trained it a bunch. They all start at 0, but we've trained it a lot. And, things have gotten negative or positive based on certain outcomes, right? So now we can say our Q table, let's say our Q table is now information dense, right? It previously had, just let's go back really quickly. So previously just had this information. Oops. How do I share that? How do I share this with myself? Can I airdrop this? Anyway, I'm still trying to work out the iPad, but yeah. Once you fill out this Q table, you imagine there's more and more information about what's good, what's bad, in terms of actions to take. Given any action state pair, what is a good and bad situation? So in the beginning, our Q table is useless since it gives arbitrary values. Oh, okay. So they have a really good example here. As we explore the environment, we update our Q table, it gives us better and better approximations. Okay, this is a very good course, very good diagrams. It's like super good with the pacing of this course. So after training, you have this information, and this is a Q learning pseudocode. This is what we saw before, and that's the recap. So what we're taking away from this is like the mental model that every state and action pair can have some number associated with it. Not zero, but some number, positive or negative, that gives us information about how good being in that state and taking these actions are.